So today I'm going to talk about a project I was able to work on during my last rotation of co-op, and that is implementing safety interlocks for pumps with flammable and combustible fluids. So a little bit of background before we get started is, it's a common industry standard to have minimum flow protection. That's usually preventative interlocks on pumps that are moving flammable or combustible fluids. And this is to prevent situations where we could have highly volatile or, in extreme cases, auto-ignition scenarios. This is most common with centrifugal pumps. And the minimum flow is defined as the lowest continuous flow allowable for a pump to operate. And this is usually determined by the manufacturer itself. And typically it can be observed, the minimum flow can be observed just as the pump is deadheaded or the discharge has been restricted. So a couple definitions I'm going to go over real quick because they're going to be terms that are brought up quite a bit through the rest of this presentation. So first off, flammable fluid and combustible fluid. So a flammable fluid is any liquid that has a flash point below 100 degrees Fahrenheit, and a combustible fluid is any liquid or substance with a flash point at or above 100 degrees Fahrenheit and below 200 degrees Fahrenheit. Now, the flash point is the temperature that the compound or substance produces enough vapor to ignite in air under standard conditions. And then an auto-ignition temperature, that's the lowest temperature that a substance will spontaneously ignite in air without an external ignition source. That could include anything from a spark to a flame. And then I'm going to refer to deadheading a lot. So when we talk about deadheading, that's when the discharge flow of a pump, so on the outlet side of the pump, is restricted. That usually happens when there's a closed valve or there's some issues with the suction pressure inside the pump. So kind of the issues that we're going to dive into is, so when a pump's been deadheaded or it reaches minimum flow, the fluid inside cannot exit the pump, so it just continues to rotate and spin inside the pump housing. So then the energy that's required to rotate the shaft and the pump impeller that's generated by the pump motor is transferred mainly to the fluid inside, causing an extreme rise in temperature that will begin to make the fluid vaporize. And then if there's not any interlocks, that will automatically shut this pump down. In this kind of scenario, the vapors could eventually reach the point where the material would fully flash off to the vapor, and then they could effectively auto-ignite, which could lead to some serious negative outcomes, including just combustion of the vapors or, in worst case scenario, an explosion inside the pump. So here's some examples of some common substances and their flash points, just to give you a better idea. So like propane is a negative 156 degrees Fahrenheit. That's an extremely low flash point, which means the vapors from propane are basically ignitable under most circumstances, whereas when you go up to somewhere like toluene or styrene, those are still pretty low flash points, but it takes a lot higher of a temperature to ignite the vapors. And the video here is just a demonstration that using canola oil that shows the different stages between flash points, your flame points, and your auto-ignition temperatures.
All right, you hear that? Watch it, bro. That's our flash point. That's our flash point. Now watch, I'll get it to 6:30. Y'all see it? Yep. Now look, we got active flames. So we already went from our flash point to our flame point. This is our flame point. But if I put it out, cover it up, it stays out. We keep on heating this up though. That's our flame point. What do we want to keep doing at this point? That's our auto ignition. At this point, we can cut the supply off, but it's hot enough, even without a direct flame, where it'll catch on fire all by itself. And it's turbulent, it's moving around, it's trying to get going.
So next I'm going to get into very simple fluid transfer example and then how this all relates to thermodynamics. So if you have some storage vessel with a flammable fluid in it and you're pumping that to some reactor and ultimately the rest of the process, when I am explaining a deadheaded situation, that just means that the discharge valve again on the outlet side somehow gets closed or there's issue with suction inside the pump. So that's when the fluid can't exit, and then you're left with a situation where the fluid can begin rising in temperature, and you can ultimately hit those flash points, flame points, or the auto ignition point. So we begin looking at like the energy boundary of the system. So if we set the boundary to just the pump and we make the system inside the pump, again, initially we have the inlet flow and outlet flow out of the pump and also some energy being added from the pump motor, but not as much since there's continuous flow throughout. Ultimately, again, when we deadhead, we have no longer a place for the fluid to go on the outlet side. So eventually the fluid will fill up the entire volume of the pump casing, thus not allowing any more to enter. So then when it gets spun around, all the energy created from the motor, well, not all of it, but most of the energy being created from the motor being added then to the fluid, and to counteract that, the fluid will begin to rise in temperature. So looking at how this relates to thermo, we can look at the first law of thermodynamics, which is, the energy cannot be created nor destroyed, or that the energy in equals the energy out. So the starting temperature of the fluid and the mass of the fluid that fills the volume of the pump can be considered the base energy of the system. And then the power being created by the pump motor can be considered the energy being added to the system over time. Again, this is based off the efficiency of the motor. Some of it's given off and heat directly off the motor, while some of it is, again, transferred to the fluid. And then the base energy plus the motor energy being added is equal to the new energy of the system, where then again, the starting temperature can be found, or the starting energy of the fluid can be found using just Q equals MC delta T, and then the pump motor horsepower is equal, or power is equal to the energy divided by time, and then again the base energy plus the energy being added can be shown as Q1 plus Q2 equals Q3, or the base energy plus the energy being added in equals the energy out, which leads to our rise in temperature. So a simple application scenario, this is a common one and one that I had to deal with myself, is we've got some specifications of a pump and then the properties of some process fluid. In this case, I've got triethylamine, or T. So using the current process conditions and the needs of the pump and using the given properties of the fluid, basically I have to find a time required to reach both when the fluid will fully vaporize or fully flash off, and then when that vapor will reach the auto ignition point, or the auto ignition temperature. This time will eventually be used to implement a timed safety interlock to shut down the pump. So the first step is to find the volume of fluid in the pump. So this can be simply found using the specific gravity of the fluid as well as the volume found of the pump to give you some mass of fluid, in this case 5.4 pounds of T, and then you can convert the horsepower of the motor into BTUs per minute just so it's easier to use. So the first thing is finding the time to reach full vaporization. So this is when all the fluid will vaporize, or the entire mass will vaporize inside the pump. You can use Q equals M times the heat of vaporization, and that's shown there. And then you can find the time to reach that by simply dividing by the energy being added from the motor based off of the horsepower to give you a time of 6 minutes. And then the next is to find when you reach the auto ignition temperature. So again, you can use Q equals MC delta T to find the energy required to reach that point, and then find the time based on the energy being added by the pump motor. So once you have these values, you need to analyze them and figure out what the next steps are going to be. So in most cases, when dealing with flammable or combustible process fluids, it's safer and more common to make the interlock delays based on the time to reach full vaporization. And this is to limit just the amount of material that could ignite in case there is mechanical failure in the system, which just means like there's a spark or some external ignition makes its way into the system. And the common standard is that a process fluid should be able to exceed 3 minutes before fully vaporizing without having to take further and further precautions. So since in this case the process fluid takes 6 minutes to reach full vaporization, it meets the 3-minute requirement and is able to begin looking at interlock solutions. So common ones are both power monitors and recirculation lines. So power monitor just continuously live monitors the power output of the motor. So if you go out in the field and you deadhead the pump on purpose and figure out what the actual power output is, because the power will drop when you reach a minimum flow point. So if you go out and figure what that is, then you can set that as a lower limit on a power monitor. So basically, once the power output reaches that low point, then a timer will kick in, whatever delay you set it to, and then if the motor can't get back over that within the time frame, then it'll shut down the pump and further investigation will need to be made. If you use a recirculation line, you could have a continuous recirculation line that just has something like a pressure reducing orifice. So if there's not enough fluid going through, or you reach a minimum flow or deadhead situation, it'll just begin pumping fluid straight back into the storage vessel or wherever it came from. Or you could have some sort of differential pressure reading between your supply tank and your outlet line of your pump. And if it reaches a certain point or a certain differential pressure between, then you could open some control valve allowing the fluid to pump back into the storage vessel so you have continuous flow, so you're not continuously just heating the same material over and over. So here are some of my sources in case you're curious, and thanks for listening.